Now let's move on to loudness. What is loudness? Loudness is the perceptual correlate of intensity. So we perceive low intensities as soft and high intensities as loud. But there's not a perfect one-to-one relationship between loudness and intensity. Loudness actually depends on frequency. An example would be if you listen to your stereo in your car and you switch it from the bass emphasis to treble emphasis, you will notice, even if you don't adjust the volume, that the sound is perceived differently depending on whether it has more low frequency information or high frequency information in it. One way of quantifying loudness is to establish equal loudness levels. So what we measure then is how much intensity is needed for tones of different frequencies to sound equally loud. So basically, does a 5 dB 1000 hertz tone sound the same loudness as, a 50 dB 1000 hertz tone sound the same loudness as a 50 dB 100 hertz tone? And the answer is no. They don't. So how is this measured? What happens is we have a reference tone that's presented at a fixed level. A comparison tone is then varied up and down in level until the patient perceives it as the same loudness as the reference tone. Then what we can do is go across frequency and do the same thing each time and plot these on a graph, and we're able to see a curve showing equal loud intensity levels as a function of frequency. So here's an example of equal loudness contours. Just to note that the lowest line is the minimum audible field line, meaning it's the lowest level at which the listener could perceive the sound when presented through speakers at the different frequencies. Now what you can see here is that a 50 dB sound at 100 hertz equals approximately 40 phones, and we'll talk about phones in just a minute. A 50 dB SPL sound at 1000 hertz equals, remember this is the 50 dB line here, equals 50 phones. So there is a difference in loudness. Okay, and let me tell you what phones are, because I'm sure you're kind of confused right now. A phon is a unit of loudness used on equal loudness curves, and it's basically the intensity to which a tone must be adjusted to match the loudness of a 1000 hertz tone at 40 dB SPL. So our reference then is a 1000 hertz tone presented at 40 dB SPL, and we describe that as 40 phons. All sounds that are equal in phons have the same loudness level, even though their actual dB SPL levels are different, are plotted along that 40 phon line because the reference is a 1000 hertz tone at 40 dB SPL. These curves are called phon curves or Fletcher-Munson curves because the researchers that developed them were Dr. Fletcher and Dr. Munson. And at 1000 hertz then, the phons and dB SPL are equal because that was our reference that was used, and that is what the curve is named in reference to. Everything on that line or that particular curve matches the loudness of that 1000 hertz reference tone. Okay? And here, okay. Low frequencies grow faster in loudness than higher frequencies, and again, you can do the bass and treble example on your stereo, or you can see it in the curves. So here's that same graph again, and if we look at this 40 phon curve, meaning that the reference then, they presented a 1000 hertz tone at 40 dB SPL as the reference, and then say they presented a 200 hertz tone, and they had the patient keep turning it up until they perceived it as the same loudness as that 1000 hertz tone, and you can see it's a little bit louder. It's like they made it equal loudness at about 42 or so. If we go lower in frequency, say we go down to 20 hertz, and we look at that 40 phon curve, follow it all the way up here to 20 hertz, we're at 90 dB. So you can see that a 90 dB tone presented at 20 hertz was equal in loudness to a 40 dB 1000 hertz tone. Now, a zone, you're getting all kinds of terminology this week. A zone is another unit of loudness, and Fond curves show equal loudness among sounds of different frequency. A zone is a unit of loudness showing the relationship between loudness and intensity. So 1 zone equals the loudness of a 1000 hertz pure tone at 40 dB SPL. 2 zones then are going to be considered twice as loud as 1 zone. What we end up with is a logarithmic scale using a ratio scaling technique. So again, a 1000 hertz, at 1000 hertz, the phones equal the zones. And as you increase intensity by 10 dB, loudness is going to double. Now this is, as I said before, this is primarily for the mid-frequencies. At very low frequencies, you get more than a doubling of loudness with a 10 dB increase. We can also talk about Stevens' power law, and I know this tends to overwhelm students. Please don't worry too much. I'm not going to have you calculate these out. I just want you to be exposed to it, okay? And what Stevens' power law does is it relates loudness to intensity. So loudness, represented as L in the equation, equals a constant value, which is K, times Li, which is the intensity, and then raised to a power, which is E, which represents the slope of the line that relates loudness to intensity. Now that sounds like a lot, but basically what you need to know is the exponent is the critical part here. And the exponent indicates the rate at which sensation level grows with intensity. So if the exponent equals 1, the sensation increases at the same rate as intensity. If the exponent is less than 1, sensation grows at a slower rate. Loudness grows at a slower rate than intensity. If E is greater than 1, the sensation grows faster than intensity. So examples would be brightness, or the perception of light, has an E less than 1, whereas electric shock, or heaviness, has an E greater than 1. As we talk about loudness, we can also talk about critical bands and loudness. Loudness changes with the bandwidth of a sound or the bandwidth between sounds. So example 1, we have 2 tones, 1000 and 105 hertz. They are 5 hertz apart, and this is called bandwidth. If you increase the frequency difference between them gradually, loudness doesn't change until they are separated by a specific bandwidth. Again, you're separating the distance between the two, and eventually there's going to be an increase in loudness. And once that increase in loudness occurs, you've reached that critical bandwidth. Again, once you get to that critical bandwidth, you'll hear a dramatic increase in loudness even though the two tones have not changed. So here's an example. We have one noise with a bandwidth of 20 hertz. If you increase the bandwidth of the noise gradually, loudness doesn't change until the bandwidth reaches a specific critical bandwidth. Once you get to that bandwidth, you hear a dramatic increase in loudness even though the noise has not changed in any way except the bandwidth. So you can see it in this graph here. It has a narrow bandwidth. As you're moving along, the intensity of the noise has not changed at all, and once you reach that critical point where the frequency difference between the two sounds have changed to that critical bandwidth, you have that increase in loudness even though the intensities of the two tones have not changed one bit. So basically, critical bandwidth is bandwidth at which a perception change occurs. We notice a big change in loudness when we reach that critical bandwidth. Critical bandwidths are larger for high frequencies and smaller for low frequencies. So an example, we have to have a larger spread between the two frequencies in a noise before we hit that point where loudness increases for high frequencies than for low frequencies. They can be closer together in frequency and we still get that jump in loudness. This type of study gives us information about the frequency resolution of the ear and how the ear handles sounds as they come in and how they're processed. Here's another graphic just to help you. We have frequency across the x-axis and then the change in frequency across the y-axis. So we have the width of the critical band, and then we can look at the critical ratio or the ratio between the two, what is needed for that change to occur. We can also talk about loudness adaptation. And our auditory systems actually adapt to loud sounds. Decrease in the loudness of a signal that is continuously presented at a fixed level for a long time occurs. So we're listening to a sound that's at a certain level, and we listen to it for a long time, and then say, okay, let me try again. Say we present a sound at, I don't know, 1,000 hertz at 60 dB, okay? And we're presenting that sound, and we have someone match a second tone to the loudness, where they're going to be pretty close to 60 dB. Then we take off the comparison tone, let the person continuously listen to that reference tone of 1,000 hertz at 60 dB for, say, a minute. And then we come back, and we have them match the loudness again. They're going to perceive the loudness differently. The actual intensity remains the same, but is actually perceived as softer. An example of this would be when you first walk into a concert, it seems really loud to you. But as you stay there over time, it doesn't seem as loud. And that's because you've had loudness adaptation occur. Well, here's an example of what I was talking about. This is time along the x-axis, and this is level of the comparison tone on the y-axis. In this example, they used an 80 dB tone. So the comparison tone was matched to the reference tone at 80 dB. They left the reference tone on, but turned off the comparison tone. And then after 5 minutes, they came back in and had someone match the loudness again, and they matched it at 50 dB. So basically, the person's perception was that the sound had decreased in intensity by 30 dB, even though it had not.